Hello and welcome to this presentation related to an introduction to beam bending deflections. This presentation does assume you've seen previous presentations related to calculation of bending moment distributions along a simply supported beam when the beam is subject to a combination of point loads and uniformly distributed loads, UDL loads. We also in previous lectures calculated bending stresses in such beams. So along with the calculation of stresses induced within beams, and thus the assessment of strengths, bending strengths, an engineer is also interested in the maximum deflection that occurs within a beam, which can be considered essentially a measure of the beam's stiffness. In the diagram shown, this is the deflection of the beam, when a force F is applied at the middle, and the beam spans length L here. This would be classified as a simply supported beam having two reactions either end, and in this case a point load is applied in the middle. So we're calculating the maximum deflection at the centre of the beam here over the span of L. Deflection of the beam depends on the loading, the geometry, the dimensions, the material from which the beam is made, and indeed the method of support for the beam. The main types of beams that can be considered are the cantilever beam, which has one fixed end and one free end, like a diving board beam. In this particular case we have a reaction at the wall and a fixing moment at the wall. A simply supported beam, which has unrestrained rotation at both ends, as shown here. We have unrestrained rotation at the ends, or a fixed in deflection at the end, no vertical movement allowed here. And sometimes we analyse encastre beams. These are beams where both ends are rigidly built in. If you like, the ends are encased in concrete. That's shown here, where we have fixing moments at either end of the beam in the wall and also vertical reactions. They're actually termed statically indeterminate beams. However, due to time constraints, in this particular presentation we're going to focus purely on analysing simply supported beams and finding deflections along a simply supported beam given a loading distribution. The total deflection of a beam is predominantly caused by bending. There can be shear deflections in beams, but it's usually the bending effect that gives the largest deflection. When designing beams to various codes of practice, not only are maximum stresses in the beams stated, but permissible deflections are also often quoted, particularly within the structural industry, for example. So both strength and stiffness aspects of beam design must be considered, as a beam could be designed to be strong enough for a particular application, but may have large in-service deflections that may be unacceptable in actual practice. There are various techniques that we can use to calculate beam deflections. There are area moment methods, strain energy methods, matrix methods, modern day finite element methods. But in this particular presentation we're going to focus on Macaulay's method. Here's an overview of engineers' bending theory, something we reviewed in a previous presentation, EBT as it's sometimes shortened to. This was the simple bending formula we considered. The bending moment divided by the second area moment is equal to the bending stress divided by the distance to the extreme fibre of the beam, and that's equal to the elastic modulus divided by the radius of curvature. The nomenclature is shown below with the appropriate units. As in previous presentations, for the work we're going to consider, we need a sign convention for bending moments. So in this case, positive bending moment will occur at a section that tends to cause the portion of the beam to what's called sag, as shown here in figure 1. Some students call a happy face, a smiling face. When the beam is forced into that position by the applied loading, we call that a positive bending moment. And conversely, a negative bending moment, that causes the beam to what's called hog. In other words, an unhappy face, as a student once said. So applied loading, whether that is point loads, UDLs, etc., that forces the beam into that shape is considered a negative bending moment. So that's a notation we will use throughout the presentation. In this presentation, we will also need a sign convention for the slope or the gradient at a point along the beam. That will be denoted as dy by dx in our particular presentation. Some textbooks denote it as angle theta. And also for deflection, we'll denote that as y in our presentation. That's sometimes noted as lowercase delta. So if for our beam a positive value of x runs from left to right, shown here, then the deflection will be positive downwards, and the gradient or the slope will be in this orientation. If the positive x runs from right to left, as shown here, then the deflection will still be downwards, as shown here, but the gradient notation will be shown in this orientation here. Let's consider briefly relationships between moment, slope and deflection. There is quite a bit of theory behind the work we're going to consider in this presentation, and we don't really have time to review that here. So I've just outlined a couple of snippets from the theory of bending. We know from our previous simple bending equation we can have an expression of 1 upon r is equal to m upon ei by transposing the engineer's bending theory equation. It can be shown that the 1 upon r could be written as a second order differential equation, so that d2y by dx squared is equal to m divided by ei. This is known as the differential equation of flexure. And you'll see in the Macaulay's method approach, we will start each of our expressions from this second order differential equation. Just want to highlight this point to you. It can be shown from simple calculus that 1 upon r is actually defined as the second order differential equation all divided by 1 plus the dy dx all squared all raised to the power 3 upon 2. It's given without proof here. But the point I want to bring out here is that engineers often make assumptions in their work, as you know. And one of the assumptions made in this equation is that second order terms, so the dy by dx all squared, are very small. So this expression here is ignored as being negligible. So that means the entire denominator becomes 1, because 1 to the power 3 upon 2 is 1. So we end up with 1 upon r is equal to d2y upon dx squared. So we often make the assumption that for small deflections, we can use the equation 1 upon r is equal to d2y divided by dx squared, assuming the dy by dx squared is negligible compared with unity in our denominator here. So all the theory we're going to apply relates to small deflections, and in the majority of cases you would probably ever analyse, small deflection theory is quite valid. I did, however, get caught out once with this assumption, where you have large displacements, as you can get in some structures. This process then falls over because that assumption is no longer valid. And the reason why we ignore second order terms is to make the solutions manageable to undertake by hand. If we were to include the second order term here, then that means a much more complicated analysis and something we'll have to use a computer to solve. So just be aware of the underpinning assumption in all the work we're going to consider that it's related to small deflections. We assume all our beams actually have relatively small deflections compared to the span of the beam. So essentially we'll be using this equation, the bending moment is equal to ei d2y by dx squared, as the beginning of each of our solutions when we're applying Macaulay's method. This will be illustrated in the examples that follow. So relationships between the moment, slope and deflection equations. So for a beam loading arrangement, it's usual for the bending moment to be expressed in a mathematical form as a function of x. So where x is the distance from a datum point, for example, the left-hand end of the beam. So we know from the previous slide that the differential equation of bending can be expressed as, and notice I've got a negative in front of my expression here, it's just for notation purposes, negative ei d2y by dx squared is equal to m. Don't forget that E is the elastic or Young's modulus, I is the second area moment, and m is the bending moment along the beam. So if we now integrate both sides of the above equation with respect to x, effectively integrating the left hand side with respect to x, integrate the right hand side with respect to x. This produces an equation for the slope of the beam, dy by dx. So on integrating, I basically get negative ei dy by dx is equal to the first integral of the moment as a function of x. All I've done on this line here is simply divided both sides by the negative ei, so I can write dy by dx is equal to the negative 1 upon ei, and that's multiplied by the integral of m. So just slightly rearrange the equation. And if we integrate again with respect to x, this now produces the equation for the beam deflection we've denoted as symbol y. So the deflection y is equal to the negative 1 upon ei multiplied by the double integral of the bending moment expression. The table below now summarizes the previous relationships for reference. So if we commence our analysis from the bending moment expression, we can say that m is equal to the negative ei multiplied by the d2y by dx squared. If we integrate that expression with respect to x, we'll find the slope of the beam, the dy by dx at the neutral axis. So we can write that as negative 1 upon ei, the integral of m is equal to dy by dx, that's the gradient equation. And if we integrate again, we find the deflection of the beam, that's y, so negative 1 upon ei multiplied by the double integral of the bending moment expression, that gives us the deflection of the beam. Again, we need to be careful that all the work we're going to consider is based on the assumption that deflections of the beam are small compared to the length or the span of the beam. So what you'll see in all the solutions that we're going to undertake using Macaulay's method, we will start from the bending moment equation, having the d2y by dx squared term in the equation. We will be integrating to find the slope equation. We will integrating again to find the deflection equation. You'll see this illustrated in the examples that will follow.
Macaulay's method. Macaulay's method extends the differential equation of bending so it can be used for writing and solving the deflection equation of the form negative ei multiplied by d2y by dx squared is equal to m, where m is not a continuous function of x. In other words, it's a discontinuous function. Macaulay's method uses the mathematical technique of step functions. So using the expression function of x is equal to x minus a in a square bracket raised to the power of n. And note the use of the square brackets, because whilst retaining the usual algebraic meaning, so 6 outside of the square bracket is equal to 6 outside of the curved bracket, what the step function does is to have a positioning effect. So in other words, we do not include a term in any algebraic equation in Macaulay's method unless x is greater than a, where a is a number. So considering these expressions again, this expression in pure algebraic form is valid whether the x is greater than or less than 3, but with the square brackets when using step functions, if x is less than 3, we would ignore the bracket. You'll see this later in the process we apply when solving for beam deflections. Macaulay's method continued. This technique permits writing of discontinuous functions by a single expression, whereas the more conventional integration approach requires that a discontinuous function must be described by a series of expressions, one for each region in which the function exists. So in our context, that would mean a different region of the beam where we have different applied loading. So with the conventional method, constants of integration must be found for each of the expressions generated. And this is particularly time consuming. So using a step function simplifies the integration process, but we do need to adhere to the particular rules around the application of step functions. An overview of the application of Macaulay's method. So the following steps must be followed when we're applying the Macaulay method. Step 1. If any uniformly distributed loads are applied to the beam and only run partially over the beam, we must ensure that they are made to extend to the right-hand end of the beam, and a negative compensation load introduced into the equation to maintain equilibrium. So this does add slight complication when generating the bending moment across the beam, but the benefit of this method is that we simplify the overall integration process. Step 2, in our work we will always measure the x dimension from the left-hand end of the beam and then generate a bending moment expression for the beam. In step 3, we integrate the terms in the brackets as a whole and ignore these terms when the value within the bracket is negative. So that doesn't obey our general algebraic rules, but in this particular case, using step function, we must adhere to that approach. Whenever the value inside a square bracket becomes negative, we must ignore the bracket from our calculations. You'll see the applications of these steps later on in the video. Macaulay's method continued. Solution of the step-by-step equations by integration. So the square bracket equations are integrated with respect to their contents in order to preserve their identity, and the process we use for the integration is shown in table 1 for the standard integrand shown as ax to the n. So for example, if we're integrating x minus a in the square brackets raised to the power 2 with respect to x, we're actually considering that as the integral of x minus a, or to the power of 2, with respect to x minus a. So our solution would be x minus a to the power of 3, or divided by 3. And that's the pattern we're following here, the ax to the n plus 1 over n plus 1. Note that a single constant of integration, c shown in the table here, must be included at the end of each line of the integration process. So when we integrate the bending equation to form the slope equation, we will add a constant of integration, call that C1, and then we integrate the slope equation to find the deflection equation, we will add another constant of integration, C2. And again, you will see how this applies later on in the examples we're going to consider. Here's a recap of the notation we're going to use throughout the presentation. The positive sign convention for moment, shown here, for slope, shown here, and the slope will be measured in radians, and for deflection, shown here, when we're working from the left-hand side of the beam. So our x value here is positive from left to right. Macaulay's method continued. Let's consider the application of point loads to our beam and the generating of the bending moment. So in the diagram below we have 3 point loads. We have W1, that's distance A from the left-hand end, W2, distance B from the left-hand end, and W3, distance C from the left-hand end. The x dimension starts from the left-hand end and moves towards the right. What we're essentially doing is considering a point, say, at location A on the beam and working out the bending moments to the left of point A. So as always, we start with the differential equation of bending, so negative EI multiplied by d2y by dx squared is equal to the bending moment. And the bending moment as a function of x now is defined as this. We've got RL multiplied by x. So RL is the reaction at the left-hand end, and that's multiplied by x. That's a positive bending moment because the RL times the x is trying to do this to the beam. It's trying to sag the beam or make it into a smiley face as we outlined earlier. So that's a positive bending moment. If our x dimension now is considered to be past that of dimension A, shown here, looking to the left of, say, this point here on the beam, we will see RL multiplied by x, and now we will see minus W multiplied by x take away A. And that's a negative bending moment because the W1 is trying to do that to the beam. It's trying to make it into a hogging beam, which is an unhappy face. So that's a negative bending moment. If we now consider x to be from the left-hand end to this point of the beam and we look to the left, we see the RL times x minus the W1 times x minus A, and now we see negative W2 multiplied by the x minus B. And if we now consider x to be at position A and look into the left of our beam, we would see the RA multiplied by x minus the W1 multiplied by x minus A minus W2 multiplied by x minus B, and we would now see minus W3 multiplied by x minus C. So we're building up the bending expression as we move from left to right, and the x dimension is increasing. So this diagram I've added in the x minus A, x minus B, and x minus C. So here's the x minus A, here's the x minus B, here's the x minus C. Again, notice the square brackets. So when we apply this step function method, if the actual inside numerical value of the bracket is negative, we will ignore the bracket from the calculation we're considering. And again, you will see that process later on in a worked example. Call this method continued. Let's now consider uniformly distributed loads, UDLs, along our beam. And as in our previous work, we will use the symbol omega to designate a UDL. Don't forget, UDLs have the units of newtons per meter, or sometimes kilonewtons per meter. So a distributed load covering the entire span can be included in the bending moment equation, and that would be valid for all values of x. However, if the uniformly distributed load is discontinuous, with this method we must extend it over the entire length of the beam from its origin, where it starts from on the beam, and then we have to add a negative load in to compensate for the additional load on top of the beam through the extension of its length. So in the diagram below we have a UDL, omega, that runs from the left-hand end along the beam a length of A. Now as the UDL is not along the entire length of the beam, we have to, in this case, extend it along the remaining portion of the beam. So this is now the imaginary omega continuing to the end of the beam. Now obviously that's added additional UDL to the beam that is not there, so to counteract the extending UDL we have to add what's called a compensating uniformly distributed load, shown here, which is equal but opposite to the imaginary load. So the bending moment expression for a uniformly distributed load, which is partially over the beam, is shown below. Notice again we have x running from left to right here. So from our differential equation of bending we have negative EI d2y by dx squared is equal to the bending moment. And now working from left to right, so now as x increases from the left-hand end, we can generate our bending moment equation. So we start off with RL multiplied by x as before, that's positive, and we subtract from that omega x multiplied by x upon 2. This goes back to a previous presentation where we considered the bending moments on simply supported beams, where we had uniformly distributed loads over the beam. So the omega times the x is actually the force, And then the x upon 2 is halfway along the UDL run, so that's the centroid of the loading, so that's the distance. So that's a force times distance. That's negative because that's trying to hog the beam. So this second term here is essentially accounting for the UDL running along the entire length of the beam. This third term of the omega multiplied by the x minus a is considering this UDL, the compensating UDL that we've added to the beam's loading, which is equal and opposite to the imaginary loading. So once again, the omega multiplied by the x minus a is the force, and then the x minus a divided by 2 is the distance. So our moments are always forces times distances. This is the x minus a divided by 2. All we've done on this next line is simplify the term, so omega x multiplied by x upon 2 is omega x squared upon 2. And here we've got omega multiplied by x minus a in the bracket, and that's multiplied by x minus a upon 2. So that simplifies to omega x minus a all squared divided by 2. And again, in later illustrations, you'll see how we apply this approach to calculating beam deflections.
Let's review an example of Macaulay's method. So example 1 here. In part 1, we're asked to write down the bending moment expression for the simply supported beam that's shown. Here's our simply supported beam. Spans length L, has a point load applied in the middle, and it's reacted at either end. We've got to determine the expression for both the slope and deflection of the beam at its midspan. Part 2, we're asked to calculate the deflection under the load at the midspan, given that the point load P is 225 kilonewtons, the length of the beam is 4,800 millimeters, the Young's modulus is 200 kilonewtons per millimeter squared, and the secondary moment I is 363 times 10 to the 6 millimeters to the 4. So what we're going to do on the next slide is use Macaulay's method to develop the appropriate expressions, and we're going to solve for the maximum deflection in the center of the beam. This is a standard beam case you would find in any textbook or reference book, but we're actually going to go through the process of deriving the equation. So example 1, here's the solution to part 1. So the first thing we need to do in all the questions is to find the reactions. Now in this particular example, the beam is symmetrically loaded, so by inspection we can clearly see that the left hand and right hand reactions will be equal to half the concentrated load. So RL and RR, they're both equal to P upon 2. So we have our reactions, we know what these values are. We can now generate the moment equation, and I'm using shorthand notation here, notice. I'm using the y double dash notation for d2y by dx squared. Often the shorthand notation is used in textbooks just for simplification. So when you see y double dash, I actually mean my second order differential equation d2y by dx squared. And when you see y dash, that will be dy by dx. So on the left hand side of the equation, I've got negative EI multiplied by y double dash. So generate my bending expression. Don't forget we're considering the x going from left to right as always, and positive bend moments is sagging the beam. So I will get RL multiplied by x, so positive bending moment, and I will subtract from that the downward force P, and that's multiplied by, in brackets, x minus L upon 2, because the P force is actually L upon 2 in from the left hand end. So using Macaulay's step function brackets, writing as x minus L upon 2, when x minus L upon 2 is negative, we will not use that bracket. So if, for example, I was considering a location here on the beam, say AA, my x dimension would be this dimension here. And because my x is less than L upon 2, this bracket would not be valid in the equation. Because looking to the left of section AA, the P is not in the expression, it's not in the bending expression. All I see is the RL. So that's the purpose of the square brackets, we ignore that bracket if the x is less L upon 2. If I was considering a position over here, call this BB, my x dimension now be this dimension across here. So now I would see the effect of the force P multiplied by this distance here. About BB, its bending effect would be negative P multiplied by the x minus L upon 2. Now noting that the RL is actually P upon 2, I can replace the RL with P upon 2, so I get Px divided by 2, and that's minus the P multiplied by x minus L upon 2 in brackets. I call that equation 1 here. Now if we integrate the above expression, we will find the slope equation. Notice I've used the y dash notation to signify dy by dx here. So negative EI y dash is equal to, and this is standard integral. Now I'm integrating equation 1, so px upon 2 integrates to px to the 2 upon 4. That's our basic ax to the n integration. And I subtract from that the bracket integrated, so x minus L upon 2 integrated with respect to x, that becomes p multiplied by x minus L upon 2 to the power of 2 over 2. And then I add my constant of integration. I call it C1 here because there will be two constants in integration. I've termed that equation 2 for reference. And integrating again, I find a deflection equation. And that's obviously, and we denote deflection by y in this set of notes. So negative EIY is now equal to, again integrating standard form, px squared upon 4 integrated with respect to x becomes px to 3 upon 12. I'm subtracting from that and integrating the x minus L upon 2 all squared divided by 2. That integrates to x minus L upon 2 cubed upon 6, and it's still multiplied by p. Integrating constant C1 with respect to x, that becomes plus C1x, and because I've integrated for a second time, I now have to add a second constant of integration, and that becomes C2. Called that equation 3. So now I've got three equations here. The first one is for the bending moment that I generated from the beam configuration. I integrated that with respect to x to produce my slope equation, and I integrated one more time to produce my deflection equation. Example 1 continued. I'm now going to consider the boundary conditions, and for all our beams we will have boundary conditions to consider. They will relate to the deflection along the beam, or they relate to the slope. And here we're going to look for where along the beam we know a deflection or we know a slope. So there are actually three boundary conditions in this particular case. The first one is that when x is equal to 0, there's no deflection, so y is equal to 0. So that's this location here. When x is equal to 0, y is equal to 0. Remember, our x dimensions are from left to right here. Now in this particular beam configuration, because it's a symmetrically loaded, semi-supported beam, we know that the slope at the center of the span, so when x is equal to L upon 2 this time, slope at the center of the span, that must be 0. So my y dash, don't forget y dash is dy by dx, the slope of the beam, that's equal to 0 at the midspan. Beam will have no slope at the midspan. And we also know in this case that when x is equal to L, so when x is L, the value here, again we've got no deflection at that location. So I've labelled them as 4, 5 and 6 just to give them references and make them easy to refer to. What we've got to do now is to solve for the unknown constants in the equation, so C1 and C2. Once we've solved for those, we can then have equations that we can use to find the slope, any location along the beam, or the deflection, any location along the beam. So considering the conditions above, I'm now going to substitute equation 4 in this case, so equation 4, and I'm going to put it into equation 3. Don't forget equation 3, shown here was our deflection equation. So into equation 3. What we'll find then is that the constant of integration, C2, is 0. So if we refer to equation 3 on the previous slide, when x is equal to 0, y is equal to 0, then if we replace the x terms for 0, this would disappear because we're multiplying by 0, so that goes to 0. And this second term here we will ignore, because if we put 0 in for x here, then the value of that bracket will be negative, and we always ignore brackets in the Macaulay expression that are negative, so that term will disappear. If we put 0 into this equation, C1 times 0 will be 0. and of course I'll put 0 in for the y, there's no deflection when x is 0, then that term will be 0. Then we can clearly determine that constant in this case must equal to 0, so that term disappears. If we now substitute equation 5 into equation 2 for the gradient equation on the previous slide, so now we know that x is equal to L upon 2, so this will now be replaced with L upon 2. This will be replaced with L upon 2. In the y dash term, which is the gradient, will be replaced with 0, so that term will go to 0 here. We end up with this expression, 0 on the left-hand side, p is multiplied by the x, which is L upon 2, and that's all squared, divided by 4. We're taking away p, and in the bracket we've got the x minus L upon 2. Well, x is L upon 2, so that whole bracket will disappear. So we will lose this term, that will become 0. We will lose this entire term here, that will become 0. So we'll end up with 0 is equal to pl squared upon 4, which is the bracket squared, L upon 2 all squared becomes L squared upon 4, that's still divided by 4, and then we will add our C1. Next line we've got 0 is equal to, tidying the bracket up, we've got PL squared divided by 16, 4 times 4 is 16, plus C1. So now we can rearrange for C1. So C1 is equal to negative PL squared divided by 16. So equation 7 now actually relates to our constant of integration, C1. C2 is 0, but C1 has a value. So I only need 2 of my 3 boundary conditions in this case. I could have used the boundary condition 6, and I would have got the same answer if I'd used 6. But I've just used the first 2 boundary conditions, 4 and 5 in this particular case. If we now substitute equation 7 into equation 3, here's equation 3 again. Don't forget we've lost the C2 term is 0 in this case. So there's equation 3. We now know what C1 is, so we can replace C1. Here's C1 being replaced. We now got an expression we can now simplify and eventually form our equation for the deflection. So the question itself required us to find the deflection under the load. Now the load is applied here, P is at the midspan, so that's x equal to L upon 2. So all I do now is insert L upon 2 wherever I see an x. So I simply insert L upon 2. So the first term simplifies to P multiplied by L cubed upon 8. Get the figures here, divided by 12. The second term disappears because L upon 2 minus L upon 2 becomes 0, so second term disappears. And my third term here of negative PLQ divided by 32. Just simplifying this line here. Further simplification on the next line, so PL cubed divided by 96, 8 times 12 is 96. And we're subtracting from that PL cubed divided by 32. What I've done here is provided a common denominator for both terms so I can add them together. And I end up with an expression of EIY is equal to PL cubed divided by 48. If I rearrange that now to find the deflection Y, that'd be deflection under the load Y, that's PL cubed divided by 48 EI, where E is the Young's modulus and I is the second area moment. I now have an expression to find the deflection at the centre of the beam. So example 1 continued, this is part 2. We're now asked to calculate the deflection under the load at the midspan. I'm given in the question the P is 225 kilonewtons, so that's the load applied in the middle. So my concentrated point load P is 225 times 10 to the 3. I'm given the length of the beam. Length is 4,800 millimeters, so I've got the L. Don't forget the L is cubed here. That's divided by 48, multiplied by the E. The E is 200 kilonewtons per millimeter squared, so my E value, 200 times 10 to the 3. And I'm also given the I value, which is second area moment value, 363 times 10 to 6 millimeters to the 4. So that's the I value here, which I've put into my equation. That evaluates to give me a deflection under the load in the midspan of 7.14 millimeters. Obviously in the design office you would simply look up the formula of PL cubed upon 48 EI to calculate deflection, but we've shown here with Macaulay's method how we can derive such a formula. The process you've seen there is the process we're going to go through in every question. In most solutions we would be using numerical solutions, not algebraic solutions.